Welcome to the next lecture on power system analysis revision. In previous lecture we have seen fault analysis. Now in this lecture we are going to see power system stability. So the first important thing in power system stability is the rotor dynamics. So that means we need to see what is kinetic energy, what is momentum, and what is inertia constant and the relations. Okay, the first very important thing or basic thing is the kinetic energy stored in synchronous machine at synchronous speed. Now this is the formula for kinetic energy stored in synchronous machine, but at what speed? Synchronous speed. So the formula is half into J into omega Sm square into 10 power minus 6 megajoules. You can also say G into H, otherwise half into M into omega S, otherwise 2.31 into 10 power minus 10 WR square product and multiply with Ns square in megajoules. See, in this case here WR square is what now? See, that is a moment of inertia of the rotor which is given in Lubin feet square. Okay, W indicates weight, that is in lubens, and radius of the rotor in feet. So that's why Lubin feet square. Okay, so if the WR square product is given in Lubin feet square, now you can use this formula directly. You can get the kinetic energy in megajoules. Okay, so but fundamental formula is this, where J is what here? J is the moment of inertia of the rotor in kg meter square. Omega Sm is the synchronous speed in mechanical radians per second. Careful, it's mechanical radians per second. Okay, now what is omega Sm? 2 pi ns by 60, where ns is the synchronous speed, that is 120 f by p. Okay, now fr is the rated frequency, where p is the number of poles. Now if you want to calculate the synchronous speed in electrical radians per second, then you must multiply with p by 2, pair of poles. Okay, so electrical equal to p by 2 times mechanical. So if you solve this by substituting omega Sm equal to 2 pi ns by 60, we get 2 pi f. And one more thing, the m is what here? Momentum, that is in megajoule seconds per electrical radians. This is the m in momentum and megajoule seconds per electrical radians, and G is the MVA rating and H is the inertia constant. You know all these things. G is the MVA rating in MVA, H is the inertia constant in seconds. Otherwise you can say megajoules per MVA, or megawatt second for MVA, or kilowatt second for kVA, watt second for VA, or simply second. All the units are same. That's about the kinetic energy formula. But sometimes he will ask you what is the kinetic energy at 1/5 of synchronous speed, 1/3 of the synchronous speed, whatever it may be. But careful, the kinetic energy is always directly proportional to rotor speed square. If really rotor speed is synchronous speed, then the kinetic energy is also what? At rated value. Rated value means KES. Okay, so depending on the rotor speed, the kinetic energy actually stored in the machine will decrease, but this is the rated kinetic energy, because default the rotor speed is synchronous speed. Clear? So now we will go to the next formula, that is momentum. See, momentum formula is, the first formula is this, J into 2 by P whole square into omega S. Omega S means in electrical radians per second, whose value is 2 pi f. Okay, so the units is megajoule seconds per electrical radian. Otherwise megajoules can be written as megawatt second. That's why you can get megawatt second square per electrical radians. Now we can have another formula also. We know that the kinetic energy stored is half into m into omega S. So using that we can write m equal to what? M, if you keep here 2 times the Ks by omega S. That's what I written here. But Kes means GH and omega S means 2 pi f, 2 to get cancelled. So this is the very famous formula for momentum, that is GH by phi f, and megajoule seconds per electrical radians. If you want to write megajoule seconds per electrical degree then here you need to substitute what? 180. If you substitute pi as 180, and the units will be megajoule seconds per electrical degree. Should be very careful with the unit, because sometimes he will ask you what is the momentum in megajoule seconds per electrical radians, what is the momentum in megajoule seconds per electrical degree. So based on that the formula must be taken accordingly. Okay, now m in per unit form also we can write. M in per unit form means we have to divide with what? Base MVA only. So if you divide with base MVA, GG get cancelled, we get H by phi f, second square per electrical radian. If you want second square per electrical degree, that pi must be substituted as 180. So that's about the momentum. These formulas are very important, and the units also. Careful about this. Then after that, inertia constant H. See, the inertia constant is defined as the kinetic energy stored at synchronous speed divided with MVA rating. So KES by G, so that's why megajoules for MVA. Megajoules can be written as megawatt second for MVA. If you divide 1000, numerator and denominator value will not change, but the units become kilowatt second per kVA. Otherwise watt second for VA are simply seconds. Now that's the units for inertia constant. Okay, clear? So basically we have what? Kinetic energy, momentum, and what? Inertia constant. These are the three things which are very, very important, and the relations also. Clear? The next important thing in stability is swing equation of synchronous machine. The swing equation is basically a non-linear equation, and also it is a second order differential equation, and that explains the rotor dynamics. Okay, now if you notice here, this is the swing equation in mechanical terms, J into d square theta by dt square, that is equal to mechanical torque minus electrical torque, and you know the units, Newton meters. Torque units are Newton meters, where theta is the rotor angular position, is measured in mechanical radians with respect to stationary reference axis. Again I am saying theta is the rotor angular position measured with respect to a stationary reference axis, and this is in mechanical radians. Okay, now theta m is the mechanical torque in Newton meters, theta e is the electrical torque in Newton meters. Accelerating torque, whatever the difference between Tm and Te, that is called accelerating torque. Okay, so that is also in Newton meters. And alpha m is the mechanical acceleration or angular acceleration in mechanical radians per second square. You may say mechanical acceleration. Electrical acceleration is Pa by m. Mechanical acceleration is Ta by J. Anyway, so that is in mechanical radians per second square. Okay, so and in electrical terms we can write the swing equation as, if you notice here, yeah, m d square delta by dt square, that is equal to Pm minus Pe megawatt. If you want to write in per unit, this is a formula in per unit. M in per unit, d square delta by dt square, that is equal to Pm minus Pe, that is in per unit. Otherwise M in per unit is nothing but h by phi f, that's what I substituted here. Okay, now what is Pm minus Pe? That is called accelerating power. This is called accelerating power, and that divided with m will give you acceleration in electrical radians per second square. And acceleration is very, very important here, sir. So let's see, based on the units we can write like this. Alpha is the acceleration, no doubt, electrical acceleration. Pa if you substitute in megawatt na, and m must be substituted as gh by phi f, so the answer will be electrical radians per second square. Suppose if you substitute Pa is in per unit na, then m must be h by phi f, careful, and the units will remain same. Suppose if Pa is in megawatt, and if you substitute gh by 180 f ms, then we get electrical degree per second square. Suppose if Pa is in per unit and m is substituted as h by phi f, and then we can get here, this is h, this is not pi, careful, this is 180. Then we get electrical degree per second square. Okay, now similarly we can write the accelerating torque. Accelerating torque equal to accelerating power divided with synchronous speed in mechanical radians per second. Okay, that gives accelerating power. Okay, and the next important thing is, yeah, before that, suppose if acceleration alpha is maintained constant, if acceleration alpha is maintained constant for t seconds, within this t seconds there is a change in load angle. The formula I am directly giving, sir, 1 by 2 alpha t square. Okay, there is a change in rotor speed, that is alpha by 3p into time. See, these two formulas are valid if acceleration alpha is maintained constant. And one more important thing is the del delta variation with respect to time is non-linear, you may say hyperbola, and change in rotor speed variation with respect to time is, for constant acceleration we get a linear curve, but this is parabola, this is linear. You may say it's a non-linear, and here it is linear. So you can find out the new rotor speed and new load angle. Okay, what is the new load angle? If the acceleration is maintained constant, initial load angle plus delta delta. What is the new rotor speed if the acceleration is maintained constant for t seconds? Ns plus or minus delta n. When we take here plus symbol if there is a acceleration, and minus symbol if there is a deceleration. Okay, so that's about the first important thing in power system stability. Now second thing is, for generator action, if you see, always the rotor angular position is ahead of synchronously rotating reference frame. This is a stationary reference axis, just for understanding I written here. So from here this is rotating at synchronous speed, that's why initially these two are coincident. With respect to time, the phase angle between these two will be omega sm into t, where theta is the angle which is measured with respect to stationary reference axis. I mean rotor angular position measured with respect to stationary reference axis, and delta is the rotor angular position with respect to synchronously rotating reference axis, and this is the relation. Okay, clear? Anyway, if mechanical power is greater than electrical power, always accelerating power is positive, rotor is accelerated. In that case, rotor speed will increase. If Pm less than Pe, accelerating power is negative, then definitely rotor is what? Decelerated, and rotor speed is decreasing. And then if Pm equal to Pe, for example, accelerating power is 0 and the rotor is neither accelerated nor decelerated, and the rotor speed is always maintained constant. Okay, clear? And the next one. For example, if rotor speed is greater than synchronous speed, then what happened? If you see these two, this is the rotor angular position and this is synchronously rotating reference frame, both are rotating in anti-clockwise direction. For example, if rotor speed is equal to synchronous speed, this angle is maintained constant. That is the third statement here I written. If rotor speed is synchronous speed, this angle is maintained constant. Suppose if this fellow is rotating with more speed, then what happened? Angle will increase. That's what. If rotor speed is greater than synchronous speed, angle will definitely increase. If rotor speed is less than synchronous speed, an angle will definitely decrease. This is for generator action. For motor action, this is exactly reverse. Because in case of generator action, if you notice here, always rotor angular position is ahead of synchronously rotating reference frame in the direction of rotation. In the direction of rotation, who is going first? Rotor, then later synchronously rotating reference frame. That means the rotor is ahead of synchronously rotating reference frame in the direction of rotation for generator action. But in case of motor action, the rotor is fall back in the direction of rotation. The rotor is rotating in this direction. Okay, synchronously rotating reference frame is rotating first, moving first, then rotor is moving later. That's why what I can say, so rotor is always fall backs the synchronously rotating reference frame for motoring action. Okay, but for motor swing equation is this: md square delta by dt square equal to Pe minus Pm. That Pe minus Pm is called accelerating power. Now for example, if mechanical power is greater than electrical power, accelerating power is negative here, because Pa is Pe minus Pm, and rotor will decelerate and rotor speed will decrease. If mechanical power is less than electrical power, then what? Pa is positive and rotor will be accelerated and rotor speed will increase. For example, if mechanical power equal to electrical power, then what happened? Accelerating power we get 0 and rotor is neither accelerated nor decelerated and rotor speed is maintained constant. For example, if Nr greater than Ns, if Nr greater than Ns, then rotor will be approaching synchronously rotating reference frame. That's why load angle is decreasing. For Nr less than Ns, load angle will increase, and Nr equal to Ns, the load angle is maintained constant. Okay. Now the next important thing is coherent operation and non-coherent operation. But before that, we see multi-machine system. Multi-machine system means if you have more than n machines or more than one machine is running in parallel, then we must convert the swing equation of all the machines onto a common base. That means you must convert on left side of the swing equation and right side of the swing equation onto a common base. See, first of all, we have to convert H onto a common base. How to convert H onto a common base? For example, H machine is given on what? G machine. H is given by considering machine rating as base. Now I want to calculate H system on what base? G system base. For that we have a simple formula. H system, that means the inertia constant on system base, is equal to G machine into H machine by G system. Okay, so like that you can convert every machine inertia constant onto a common base. So that's why, so remember one thing, sir, whenever base MVA changes, whenever base MVA changes, what will change? For example, H will change or not change? H will change. Okay, tick right mark for change, cross mark for no change. Okay, M in actual form, M actual means what? Will not change. M actual means megajoules seconds per electrical radian. It will never change, remain same. Then M in per unit form, M in per unit form definitely will change. M in per unit form means what is the units? Second square per electrical radian. That will definitely change. And next, alpha acceleration, that will never change. So H will change, M in per unit form will change, but M in actual form, alpha will never change if there is a change in base MVA. Careful about this, this is very, very important. And so coherent operation and non-coherent operation. Suppose if two machines are running in parallel, okay, then what is coherent operation and what is non-coherent operation we need to understand. Coherent operation means all the machines are swinging together. Non-coherent operation means if the machines are swinging in opposite directions. For example, generators are running in parallel. It's called what? Coherent operation. Generator and motor running in parallel, that's called what? Non-coherent operation. For example, motor and motors are running in parallel. Again, that is a coherent operation. That means a generator and motor running in parallel, that is called a non-coherent operation. Otherwise, it is a coherent operation. So, for a coherent operation, if you notice, the two machines having inertia constants, H1 and what? H2. They are already on common base, careful. Then H equivalent can be written as H1 plus H2 if they are on common base. Okay, clear? And so for non-coherent operation, H equivalent will be H1 H2 by H1 plus H2. But what about M equivalent? M1 plus M2. But here M equivalent will be M1 M2 divided with M1 plus M2. So indirectly what you can understand here, so M equivalent is increasing here, but M equivalent is what? Decreasing here. Because of coherent operation, M equivalent is increasing. Non-coherent operation, M equivalent will decrease. So that's why if M equivalent increases, then what happened? Acceleration alpha decreases. Change in rotor angle with respect to time decreases and stability increases. If the rotor angle is changing very slowly with respect to time, then system is more stable. And here exactly opposite, alpha increases, change in rotor angle with respect to time increases, and ultimately the stability of the power system, if you notice, that will decrease. Okay, so that's about the importance of coherent operation. Coherent operation will improve the system stability. But generally in power system we have coherent operation because we have n number of generators which are running in parallel. Next, power flowing through a transmission line under steady state. See, there is a transmission line, we have a sending end port and we have a receiving end port. We need to calculate what is the power flow at the receiving end. So PR is the receiving end power delivered, active power delivered, and QR is the receiving end reactive power delivered. Now Z is the series impedance of the line. We can write mod Z at an angle theta. What is mod Z? Under root of R square plus X square. And what is this theta? Tan inverse X by R. That is also called impedance angle. So the formula for power PR I am directly given here. Vs VR by Z cos of delta minus theta. Okay, actually cos of theta minus delta. Anyway, both are same, cos of delta minus theta or theta minus delta. Okay, clear? Yeah. So, and VR square by Z into cos theta. Cos theta can be replaced there as R by Z from the impedance triangle. Okay, and similarly the QR expression Vs VR by mod Z sine of theta minus delta VR square by Z into sin theta. These are the two expressions which are very important. And condition for PR max. What is the condition for PR max? You need to differentiate the active power. To get the condition for PR max, we need to differentiate the active power with respect to delta and equate to 0. And if I do, I will get this delta equal to theta. So from that I can calculate PR max, and reactive power corresponds to PR max. But if you notice, the reactive power corresponds to PR max is negative. What is the meaning, sir? So when the transmission line is delivering, or a synchronous generator is delivering maximum active power to the load, means load power factor is leading. Okay, receiving end power factor is leading. So to deliver maximum active power, the synchronous machine is operating at leading power factor. Synchronous machine operating at leading power factor means it should be under excited. It should be under excited. Okay, clear? Because so load has to deliver the reactive power back to the generator. That means the generator is consuming the reactive power. That means it must be under excited. But think about in terms of power system for a transmission line. If you want to deliver maximum active power to the load, load must be capacitive. Load should be capable of supplying reactive power back to the line. But practically all our loads are induction motors. 85% of the loads are induction motors. So that's why to achieve this maximum active power delivery condition, we need a capacitive compensation at the receiving end, so that capacitor can supply what the load is required and what the line is required. This is what the line requirement. Similarly, we have a load requirement QL. So the reactive power capacity of that capacitor is line requirement plus load requirement. Line requirement is 10 MVAR and load requirement is 5 MVAR, and capacitor should supply 15 MVAR. That means without capacitor or without reactive power compensation at the receiving end, we cannot utilize the full capacity of our transmission line or full capacity of generator. So that's why the idea is the shunt capacitive compensation is preferred here to get maximum utilization of transmission line or maximum utilization of generator. So that is the thing you need to notice. And the next thing is if Vs equal to Vr, and then you can substitute in PR max formula, we get this. And condition for maximum possible PR max. See, if you want to get a condition means, let's see who are the variable here. Since the transmission line means Rx, which are in series, I can control the X by controlling what? Series compensation. But if you want to control the X, yes, you are using series compensation. So that means variable is X here. So you just differentiate PR max with respect to the reactance of the transmission line and equate to 0. And finally we get this condition X equal to root 3R. That means X bar ratio equal to what? Root 3. Mod Z equal to we get 2R and theta equal to 60 degrees. Correct or not? So, but X bar ratio root 3. But in a practical system, X bar ratio is very high, which is greater than 5. So that's why we need to decrease the X bar ratio. That means you have to decrease the value of X. If you want to decrease the value of X, the best way is let's use a series capacitive compensation. The series capacitive compensation we need to use here. With the help of series capacitive compensation, we can decrease the value of reactance. That means we can decrease the overall reactance value. Okay, this is XC external series capacitive reactance. With the help of that, I can achieve this condition. The idea is very simple. XL minus XC external by root 3, sorry, by R equal to root 3. We can do it. By using an external capacitor, we can achieve this. Right? Clear? And if that is the case, what is the PR max? V square by 4R, and QR corresponds to PR maximum is minus root 3 into V square by 4R. If you see, the power factor is 0.5 leading. Okay, because we get tan inverse root 3. Tan inverse root 3 is nothing but what? 30 degrees. Cos 30 is 0.5. Okay, sorry, tan inverse root 3 is 60 degrees. Cos 60 is 0.5. That means when transmission line is delivering maximum possible active power to the load and the load power factor is 0.5 leading, that you have to understand. Next, steady state stability, sir. See, steady state stability means it is the ability of the power system to remain in synchronism if the load on the machine is gradually increased. For example, if you have a generator and there is a load, you are just increasing this load. Okay, if I increase the load up to how much power the generator is remain in synchronism, that is called steady state stability limit. That means when the load is gradually increases, then what? So the generator, the stability will be slowly decreases. At one point the generator is at verge of stability. After that, even if there is a small increase in load, the generator lose synchronism. Okay, clear? And what is the steady state stability? It is the ability to maintain the generator or to maintain the system in synchronism or to regain the steady state after it has been subjected to a gradual increase in load. Okay, so we can calculate steady state stability limit as well. So steady state stability limit means it is the maximum power that can be delivered to the system. For example, if we take a generator, this is the equivalent circuit of the generator and this is the power angle equation, you know this. But what is the condition for PR max? You need to differentiate electrical power with respect to delta and equate to 0, and I will get delta is 90 degrees. That means for stability region, maximum possible delta is 90 degrees ideally. So what is P max? Indirectly EV by XX. Correct or not? If you want to substitute delta 90 degrees, we get P max, that is EV by XC. So from that we can write dou P by dou delta is EV by XS cos delta. P is what? EV by XS sin delta. EV by XS I can replace as P max. Dou P by dou delta and power angle equation. These two are very, very important. This dou P by dou delta is also called synchronizing power. Why? Because let's see, dou P by dou delta is 0 here. Here it is positive and here it is what? Negative. See, in this region, if there is an increase in load angle means there is an increase in electrical power. For increase in load angle means there is an increase in load, there should be an increase in electrical power. If load increases, electrical power decreases means that is an indication of instability. So till here, if load increases means load angle increases, electrical power increases. But here, if load increases, what happened in this region? Load increases, electrical power is decreasing. That's why system is unstable. That means up to 90 degree system is stable, and after 90 degree system is unstable. That means the dou P by dou delta is the slope of the power angle curve. Correct or not? Dou P by dou delta is what? Slope of this power angle curve. Slope of power angle curve. That explains what? Steady state stability. Correct or not? So dou P by dou delta explains the steady state stability, and dou P by dou delta is maximum at delta equal to 0. Okay, because if you notice dou P by dou delta equation, what is dou P by dou delta equation? P max cos delta. If you substitute delta equal to 0, then dou P by dou delta is maximum. Remember this, delta equal to 0 means dou P by dou delta is what? Maximum, but electrical power is 0. Delta 90 degrees, dou P by dou delta is what? 0, but P is what now? P max. Correct or not? Clear? Dou P by dou delta is 0, but P is what? P maximum when delta is 90 degrees. Okay? Clear, sir? So that means at delta 0 degrees, dou P by dou delta is very high, system is more stable, but transferring 0 power. But if delta 90 degrees, system is what? Almost unstable, but transferring maximum power. So that means we must have a compromisation between dou P by dou delta and electrical power. The system must be stable and should supply what? Some power. Okay, that is the idea. Anyway, let's see, dou P by dou delta positive means delta 90 degrees stable system. Dou P by dou delta negative means what? Delta is greater than 90 degrees and it is an unstable system. If dou P by dou delta is 0 means delta equal to 90 degrees, marginally stable system. Okay, have a look here. Yeah, I told you just now, for delta 0, electrical power is what? This is electrical power, this is dou P by dou delta, also called synchronizing power coefficient. Okay, so if delta equal to 0 degrees, we get dou P by dou delta maximum, but electrical power is 0. So we get a best compromisation at delta equal to 45 degrees. That is why ideal limit of load angle is what? 90 degrees. But practical limit of load angle is always less than 45 degrees, generally less than 30 degrees, very close to 30 degrees. Okay, that is the practical limit of load angle for a synchronous machine. Okay, clear? And dou P by dou delta is also called synchronizing power coefficient. We already discussed that. Anyway, for salient pole machine, we have a xd greater than xq. This is the power angle equation for salient pole machine. EV by xd sin delta plus v square by 2 into 1 by xd minus 1 by xq times sine 2 delta. So we can write C1 sine delta plus C2 sine 2 delta. I hope you understand what is C1, EV by xd. C2 v square by 2 into 1 by xd minus 1 by xq. I think this is xq, this is xd. Careful. Yeah. Next, delta max is less than 90 degrees for salient pole machine. If you see here, this is what the plot for salient pole machine, power angle curve, delta versus P, power angle curve. This is a plot for cylindrical rotor machine, this is a salient pole machine. Exactly delta max is 90 degrees here, but here less than 90, that's what I written here. Delta max less than 90 salient pole machine, careful about this. Delta max equal to 90 for cylindrical rotor machine. And P max of salient pole machine is always greater than P max of cylindrical rotor machine for same power rating. Yeah, as we already discussed, dou P by dou delta is called synchronizing power coefficient. That is nothing but K, we say K, that is dou P by dou delta, P max cos delta. Synchronizing power also sometimes you asked to calculate. In synchronous machines also you might have done this calculation, K into delta delta. But careful, after calculating K, you must be substitute delta delta in radians. But basically we calculate this K for initial rotor angle. After that there is a disturbance, means what is the synchronizing power. That is explained by this formula. Next, steady state stability from swing equation. Okay, so how to calculate the steady state stability from swing equation? See, careful, when you are solving for swing equation, generally we neglect the damping, but very rare cases damping will be included. Okay, in gate till now there is no question with the damping, but it's an untapped area. Okay, but you must understand if the damping is given, what happens. Okay, so damping coefficient Kd will be added here. This is a swing equation modified with the damping coefficient Kd. If the swing equation is in megawatt, careful sir, the damping coefficient unit Kd is nothing but damping coefficient. And what are the units of damping coefficient here? Megawatt seconds per electrical radians, otherwise megajoules per electrical radians, if the swing equation is in megawatt in actual form. If swing equation is in per unit form and Kd units are seconds per electrical radians, please notice that. Okay, clear, and that will help you in calculations. So we can calculate the damped frequency oscillations, a natural frequency of oscillations, damping factor and damping ratio. And we know that in control system, zeta equal to 1 critically damped, zeta 0 undamped, zeta greater than 1 overdamped, and zeta less than 1 means it is a underdamped case. Okay, so remember all these formulas. Okay, clear till now, there is no question on this formula. This is an untapped areas. Okay, so careful about this. Next, transient stability, sir. Transient stability deals with what? Large disturbances, followed by a large disturbance. If the system is stable, means that is called a transient stable system, followed by a large disturbance. If the system is unable to recover its synchronism, means it is a transient instability. Okay, large disturbances means sudden change in load, faults on the power system. All this comes under large disturbances in power system. But what are the assumptions for transient stability? The first assumption is generators are modeled with transient reactance. But if you really notice, for generator operation, so we have a subtransient reactance, transient reactance and steady state reactance. But generally the generator is modeled with transient reactance. That's what I am saying for transient stability analysis. And change in reactance of machine due to change in frequency during disturbance is neglected. See, I hope you understand this point. See, reactance formula is what now? 2 pi f into inductance. Inductance is generally a constant, but during disturbance the rotor speed of the synchronous machine will definitely change. If rotor speed changes, the frequency also changes, because frequency is directly proportional to rotor speed. If frequency changes, reactance also changes, but that change we are neglected. And effect of governor control is neglected. That means during disturbance the mechanical input to the generator is always assumed to be constant, but actually speaking governor will control that mechanical input, but we are assumed to be constant. But generally governor effect is what? Contributing for improving the stability. Similarly, effect of excitation control is also neglected. That means E is assumed to be constant. So here PM is assumed to be constant. Damping of synchronous machine is neglected. Just now we discussed the damping coefficients Kd, that is equal to be 0. That means swing equation is what now? Md square delta by dt square, that is equal to simply Pa. Okay. And saturation of synchronous machine is neglected. That means synchronous reactance is always constant. Resistance is neglected for synchronous machine. Saliency is neglected. Saliency means what? Xd minus Xq is called what? Saliency, that is equal to 0. That means even though it is a salient pole synchronous machine, what is the power angle equation? P max sin delta. Cylindrical rotor machine anyway, that is P max sin delta. Salient pole machine also better to consider what? P max sin delta, then only analysis is easy. Now what is the swing curve? See, followed by a large disturbance, we plot the swing curve. It is a curve between delta versus time. Okay, we are just plotting the variation of load angle with respect to time. Okay, so if you notice here, initially the rotor angle is delta naught. Followed by a large disturbance, the load angle is maybe increasing like this, and after that it starts decreasing. Then this is the new rotor angle or new settling angle delta 1. Now this is what? Delta 2, and similarly there exists what? A delta max. Now that delta max equal to 180 minus delta 1. The idea is very simple here. Initially rotor angle is delta naught, followed by a large disturbance. If rotor angle is increasing, then it start decreasing now. That's enough to conclude system is stable. Followed by a large disturbance, if the rotor angle is continuously increasing like this, and this is called unstable variation. Okay, now this is what? Stable variation. So the idea is very simple. Followed by a large disturbance, you just see the load angle variation. If load angle variation is continuously increasing till delta max, after that also increasing, that's enough. You can directly conclude that system is unstable. If load angle is coming up to delta max and then start decreasing, marginally stable. If the load angle is coming up to some delta 2 which is less than delta max, then what? Start decreasing means system is definitely, absolutely stable. So just see here, delta naught is pre-disturbance steady state rotor angle. Delta 1 is what? Post-disturbance steady state rotor angle if system is stable after the disturbance. Delta 2 is the maximum rotor angle or maximum excursion of rotor angle during oscillations or before settling to new steady state operating point. Okay, delta max just now we defined. And what is the importance of delta max? See, if the rotor angle increases and if it is increasing above delta max, then you can say system is unstable. Okay, so and slope of the swing curve is d delta by dt, sir. The slope of the curve, there exists a d delta by dt equal to 0 for a stable system. Here it is 0, but unstable system is d delta by dt is always positive. Okay, clear? That means from the slope of the power angle curve we can conclude steady state stability. From the slope of the swing curve, that is d delta by dt, we can conclude transient stability of the system. Clear? Now equal area criteria, sir. What the equal area criteria is saying? Followed by a large disturbance, if the area under the PA delta curve, PA d delta curve is 0 means, then that's enough to say system is stable. But careful, so when this is correct, acceleration area equal to deceleration area, then only the area under the PA delta curve, PA d delta curve is what? 0. Okay, clear? Understand? So, and first important thing is equal area criteria, if you notice, valid for single machine system, single machine infinite bus system. In short we say SMIB, and not valid for multi machine infinite bus system, but also valid for two machine system. In that case no infinite bus. Careful, it is not valid for multi machine infinite bus system, but it gives what? Absolute stability of the system. Okay, clear? Now there is a case study. The mechanical load on the motor is suddenly increased. See, this is what the initial mechanical load on the motor. Now mechanical load is suddenly increased from PM0 to PM. So but at point A initially the rotor is operating here with some rotor angle delta naught under steady state. So that's what I written. But suddenly at point A what happened? Mechanical load is increased from what? PM0 to PM. That means electrical power is what? Here only. PE less than what? PM. So rotor decelerates here. Why? Because mechanical load is more than electrical power. Then rotor speed is what? Equal to synchronous speed but decreasing trend. Load angle equal delta naught only but increasing trend. That means we are in forward swing. Correct or not? Then what I can say here, from A to B, since we are in forward swing from A to B, what happens A to B in this region? Mechanical power is more than what? Electrical power. Accelerating power is PE minus PM. Na? Since mechanical power is greater than electrical power, again what now? Rotor is what? Deceleration only, and rotor speed is here equal to synchronous but decreasing trend. But what happened here? Less than synchronous, but because of deceleration it is in what? Decreasing trend. And load angle is what? Greater than delta naught. Okay, this is not less than delta naught. Load angle is greater than delta naught but what? Increasing trend only. Okay, but at point B, mechanical power equal to electrical power and accelerating power is 0. Okay, at point B, rotor is neither accelerated nor decelerated. But careful, shall we settle here? No. Why? Because at this point rotor speed is what now? Decreasing and it is becoming what? Less than synchronous speed. Ultimately rotor speed is less than synchronous speed minimum here. Okay, because after that point rotor speed is what? Going to increase. But load angle is what now here? Delta 1, but it is increasing trend. Why? Rotor speed less than synchronous speed means always load angle will increase. Okay, clear? Now after that from B to C what happens here? Electrical power is greater than mechanical power. Now the reverse operation. Rotor speed what? Increasing trend but less than synchronous speed only. Suddenly it will not catch the synchronous speed. So load angle also increasing trend. Why? The rotor speed is less than synchronous speed. At point C, why I am assuming point C here? Because at this point rotor speed is recovered to synchronous speed. Why? Because here in the forward journey here rotor speed is less than synchronous speed and also what? Increasing trend. That's why it may catch the synchronous speed maybe at point here. Okay, so if the rotor speed is catched at synchronous speed but increasing trend only, why? Electrical power is greater than mechanical power. So load angle is what now? Delta, but load angle is constant, but a moment later it starts decrease because of rotor speed is going above synchronous speed. Why? Because rotor speed is increasing trend. If rotor speed is going above synchronous speed means what happened? Rotor speed greater than synchronous speed means load angle is decreasing. Motor action less than synchronous speed, load angle will increase. For motor action I am writing, sir. And if you notice later at C to B again, because earlier forward journey, now it's a backward journey. Again rotor speed is what now? Greater than synchronous speed but increasing trend. Load angle is decreasing at point B and again B to A and finally at A. So that means the rotor speed is here synchronous speed and here synchronous speed. And here in forward journey less than synchronous speed minimum, in backward journey greater than synchronous speed maximum. At point B I am talking. Okay, so with respect to time what happened? See, these 2 points are approaching to B and finally rotor speed at B will be synchronous speed. In the first swing this, second swing it will come up to here, third swing, fourth swing, fifth swing, something like that, and finally at point B only machine will settle. Okay, so that's what the conclusions I written here. Have a look. During disturbance rotor is swinging from A to C and finally settling at what? B under steady state. That is the idea. At B it is settling under steady state. During forward swing, swinging from A to C, at A and C rotor speed is synchronous speed, but at B rotor speed is less than synchronous speed and minimum. During backward swing, that is C to A, at A and C rotor speed is synchronous speed only, but at B rotor speed is what? Greater than synchronous speed. If system is stable after disturbance, then under steady state at point B the rotor speed is recovered to synchronous speed and there is no concept of A and C under steady state. All these points are merged at what? B, A, C and going towards B. That is the idea. Okay, clear? Now basically transient stability calculations are, we have to calculate the stability of the system for a given increase in load, calculation of transient stability limit, calculation of maximum rotor angle, and by how much load suddenly increases without loss of synchronism, and critical clearing angle and critical clearing times. So these are the things we calculate from the transient stability analysis. Now quickly determining of the stability. The idea is what here? The load on the machine is earlier PM naught. Initially load is PM naught. Now it is increased to what? PM. Then we have to comment on whether the system is stable or not. So to comment on system stability, let's see, this is what mechanical power and electrical power, and this area is called accelerating area, decelerating area. Mechanical power is greater than what? Electrical power. And this is what available deceleration area, that is called A2 dash, because we are going up to delta max. Delta max is 180 minus delta 1, where delta 1 is the new steady state rotor angle. So how to calculate that? PM equal to P max sine delta 1. From here we can calculate delta 1 value. Okay. Yeah. So after calculating delta 1, you can calculate these two areas, A1 and A2. After calculating A1 and A2 dash, if A2 dash is greater than A1, then system is stable. A2 dash is less than A1, system is unstable. A2 dash equal to A1, then system is marginally stable. That is how we can calculate. Next, calculation of transient stability limit. Remember sir, always it is 72.46% of steady state stability limit. That means P max. Okay, irrespective of whatever may be the given P max, this condition is always true. So what is transient stability, by the way? So if the load is increasing suddenly from 0 megawatt to PM megawatt, system is at verge of stability. System is at verge of stability means load angle delta 2 equal to what? Delta max, and rotor speed is recovered to synchronous speed exactly at what? Delta max. That's called verge of stability. That means A2 dash equal to what now? Exactly A1. Okay. Now the corresponding PM, this PM is nothing but transient stability limit. Okay. And you can calculate the delta 1, and from there I can calculate it. PTSL is 72.46% of steady state stability limit. And calculation of maximum excursion of load angle. See, to calculate the maximum excursion of load angle for a given load change, that means the question will be given like this. Initial load is 10 megawatt. Now the load is increased by 30 megawatt. That means the new load become 40 megawatt. Then what is the maximum rotor angle achieved by the rotor, or maximum excursion of rotor angle is asking. To calculate that, again you need to equate area A1 and what? Area A2. So after equating area A1 and area A2, let's calculate delta 2. Now that is the final answer. Okay. And then by how much load suddenly increased without loss of synchronism? Okay, to calculate that, if the load is PM naught initially, maybe I am assuming that this much load I can suddenly increase it without loss of synchronism. Means what? So for increasing of that load, this area A1 and A2 dash become same. That means the rotor speed is recovered to synchronous speed exactly at delta max. That means delta 2 equal to delta max. So again equating A1 and A2 dash, let's calculate delta 1. Then PM also you can calculate, but answer is PM minus PM naught, because he is asking by how much load suddenly increase. That means this much load suddenly increase such that the rotor speed is recovered to synchronous speed exactly at delta max, and delta 2 equal to what now? Delta max, and system is marginally stable. So that's why this much load, the gap, whatever it is called, that is by how much load that is suddenly increased without loss of synchronism. Okay. And calculation of critical clearing angle and critical clearing time. Sir, so to do this, depending on the type of fault and location of the fault, we can do, sir. So, so these are the formulas which is written for the third case. If you notice, the fault is at the middle of the line. In that case, there exists a pre-fault maximum power transfer, post-fault maximum power transfer, and during fault maximum power transfer. This is what? Pre-fault, during, post-fault. Okay, clear? So based on that we have a formula, and also we can see what if the fault is very close to the bus bar and what if the fault is on the bus bar. But careful, if the fault is on the bus bar and very close to the bus bar, P max 2 is what? 0. Okay, clear? P max 2 exists only if the fault is at middle of the line. If the fault is very close to the bus bar, P max 2 is 0. Okay, if the fault is very close to the bus bar, for these two cases only TCR formula is valid. And what is the formula for that? 2H into delta CR minus delta naught by pi F and PM square root. Okay, but for third case, if the fault is at middle of the transmission line, for this case critical clearing angle is calculated using numerical integration techniques. So review all these concepts which are very important, sir, and I am going to conduct a test on stability and load flow analysis in tomorrow's session. Okay, be ready for that. And load flow analysis are very simple. Okay, you just review that, only simple formulas, Y bus, and also what? So calculation of Jacobian size, nothing else in load flow analysis. Okay, I'm not going into that, but I will give the questions on load flow analysis as well in the tomorrow test. Just go through it. It's very simple, nothing great. Thank you.